Audio Jungle. Audio Jungle.
Okay, so for incompressible aerodynamics, and as I had discussed about types of the aerodynamics, okay, so types of aerodynamics in the sense what? It will go for the based on analysis of the flow, it is so basically two types we have incompressible and compressible and compressible, okay. So incompressible aerodynamics, and this is what compressible aerodynamics. Fine. Right. So incompressible aerodynamics, as I had mentioned, will have two three things. Number one, density must be constant; it is not going to change. Number two, it is like a low speed flow, or in terms of Mach number, it is less than zero point 0.3, and this is what low speed aerodynamics. Okay. Similarly, this is what compressible aerodynamics, where it is ready to compress, means density will not be constant, okay, and Mach number will be greater than 0.3, and it is called high speed aerodynamics. All right. High speed aerodynamics. So now our topic is what today? Incompressible aerodynamics. This is our focus basically. Okay. Incompressible aerodynamics. So what do you understand by the incompressible? Incompressible means density is what not going to change, means density is what constant. If this is the flow field, check, this is the flow field here. This is called flow field. Okay. So throughout the flow field, density must be constant. Okay. Density must be constant. Any 2 points you can consider, point number one and this is point number two. Say density here rho one as per point, and density is what rho two as per point two. And for incompressible flow, rho one is equal to rho two. That means it is constant. This is what flow field. Okay. Flow field. Fine. This is the incompressible aerodynamics. So just like an incompressible flow, we have a different terminology, which sometimes it is called invisible flow, okay, steady flow, unsteady flow. So there are the different types of the flow. So few standards types of the flow I will explain here, then I will go ahead, so it will be better. Okay. Types of flow. What are the types of flow? Check. Steady flow, unsteady flow, okay, compressible flow, incompressible flow, and rotational flow and irrotational flow. These are the different standard types of the flow. Okay, these are the standard types of the flow in aerodynamics. Standard, okay, types of the flow. All right. So there are many. Okay, many more than 25 types of the flow, but it is not required. You have seen that in your semester. Here, especially that standard, I will explain 1 to 6 in short time of period. So, what is the steady flow? Because this terminology will come again and again. So, better let me explain this first. So, steady flow means what? Suppose this is the flow field. Okay, this is what flow field. This is the flow field here. Second, this is the flow field. Okay, and for this particular flow field, all the flow property or fluid property like density, fluid property like viscosity, okay, fluid property like bulk modulus, okay, surface tension. These are the fluid properties. All right. So for the, and what is the flow property like velocity? Okay. So acceleration also is the flow property. So angular velocity is also a flow property. So fluid property or flow property, if it is constant with respect to time, it is not going to change. It is not going to change. So what I am saying, fluid property or fluid property or flow property or flow property, if it is not going to change with respect to time, it is not going to not going to change with respect to time. All right. So if I say fluid property like density, yes or no? Temperature, all right. Pressure, fluid properties. Similarly, velocity. Okay. So if these properties are not going to change with respect to time, it means it is constant. Okay, it is constant. So if it is constant, so derivative with respect to time will be what? Zero. Derivative with respect to time will be zero because it is constant with respect to time. Yes or no? Derivative with respect to time will be zero. So these are the this type of flow. This type of flow called as steady flow means it is constant. It is not going to change with respect to time. Huh? Suppose it is at point 1, okay, and it is point 2, okay. So definitely from point 1 to 2, it will take time, 2 seconds, 3 seconds, 4 seconds. That fluid particles will take time from point 1 to point 2. Yes or no? So time is what changing after 2 seconds. If pressure is what going to change, or temperature is what going to change, or density is going to change after 2 seconds or 2 hours, flow velocity is what going to change after 2 hours. So that will not be steady flow. But if it is constant with respect to time, it is not going to change. It means it is steady flow. If it is changing with respect to time, it will be unsteady flow. Hope you understood. Yes. So steady flow and unsteady flow. If I explain steady flow, then unsteady flow is what? Just reverse of the steady flow. Yes or no? So point 2, what is the unsteady flow? It is reverse of steady flow. What is the meaning of it? Its meaning is it is it is it is going to change with respect to time. So here I must write it is going to change with respect to time. It is means what? That fluid property or flow property is going to change with respect to time. Yes or no? So if you write this, both flow property as well as fluid property, yes or no? If you check if it is going to change, that means that derivative, if you write, that will not be zero. That's not zero. Why? Because it is going to change. It is variable now. Okay. For what derivative will be zero? For constant value, derivative will be zero. But if it is not constant, it is variable, then derivative will not be zero. So it is variable. It is mentioned. It is going to change with respect to time. So time derivative will not be zero here. Yes or no? D rho by dou rho by dou t does not equal to 0. Dou p by dou t does not equal to 0. Dou temperature divided by dou t does not equal to 0. Dou velocity by dou t does not equal to 0. This is what? Unsteady flow. Okay. Similar thing. It is just reverse of steady flow. What I have explained for the steady flow, the same thing in the reverse way will be unsteady flow. Okay. Not going to change means what? Means constant with respect to time. Okay, there should not be any confusion. Not going to change means what? Not going to change means constant. Constant with respect to time. That fluid property or flow property, if it is constant with respect to time, then it is called steady flow. If it is not constant, okay, not constant with respect to time, then it is unsteady flow. I hope you understood this, right? Steady and unsteady. Steady and unsteady. What is the next? Compressible and incompressible. So that already I have discussed. There should not be any confusion. Okay. Third is compressible flow. Okay. Compressible means what? Fluid allowed compression or fluid is ready to compress. Okay. If fluid is what ready to compress, then density will not be constant, right? Okay. If density will not be constant for any fluid flow, this is the fluid flow here, or flow field, better to say flow field. For this flow field, if density is what not constant, then it is called compressible flow. It is ready to compress means what? Check. Suppose we have one piston cylinder arrangement. This is what cylinder. Okay. And we have a frictionless movable piston here. This is the movable piston here. This is the movable piston, okay, and we have fluid. Cylinder is filled by fluid, okay. Any compressible fluid means it is ready to compress. Now if it is ready to compress means it will allow the compression. If it will allow the compression, that means piston will move in forward direction. That piston will move in forward direction. Now this is the piston location. Yes or no? So your fluid, whatever the fluid available now, that fluid will be shifted. This fluid will be shifted to next position. So now volume is what decreasing. Yes or no? If volume is what decreasing, that means for the same mass, density will be, check, volume is what decreasing. Now, wait. Rho is equal to mass per unit volume. Mass is what constant. Suppose for 1 kg. So density and volume is what just opposite. See, volume is here. Earlier it was V1. Now it becomes V2. And V2 is less than V1. So just reciprocal means rho 2 will be greater than rho 1, means in second case here density will be rho 2, which will be greater than rho 1, means density is what changed. Why? Because volume changed for the same mass. So if such thing will happen, then it will be called as a compressible fluid. And during the process, during the flow, if it will happen, anyhow, then it will be called as a compressible flow. Remember two things: compressible fluid or compressible flow. So here I need to mention here compressible flow and fluid both. Okay. So compressible fluid means fluid is what? Fluid allow compression. See, if that fluid allow that compression, then only that piston moved in forward direction. Otherwise piston will not move, right? And allow compression means what? Fluid is ready to compress, and if it is ready to compress, that piston will move from one position to another position. This is the position number 1 and this is the position 2. One piston move from 1 to 2, then definitely volume will be changed. In second case, volume will be less than first case. If volume change, then automatically density is opposite to the volume, so density will change. That means density not constant for the fluid, and such type of fluid, if it is flowing in the channel, then it is called compressible flow. Compressible fluid and compressible flow. Got my point? There should not be any confusion about compressible fluid and compressible flow. Compressible fluid, if it is flowing, then it is called compressible flow. Or during the flow, if fluid is what? Compressing. Okay, there are certain reasons like when shock formation will be there, or then where there is the hammering, fluid hammering will happen like in water and all. Then there will be a compression. Okay, so like in flow, how it is going to compress, that is the secondary part. When I will go for the high speed flow, mag greater than zero point 0.3, then only I will explain how that fluid is what going to compress. So it is compressible fluid. So it is very clear. Compressible fluid means what? Max should be greater than zero point 0.3. Means if it is very high speed flow, then it will try to compress from one point to another point. If fluid will move, then it will try to compress because of the high speed, and compression occurs means automatically density will be changed, means density will not be constant. Hope you understood this. This is the 3. Okay. Now what is the incompressible? Simple, just opposite. Incompressible flow or fluid. Same thing, not allow compression, not ready to compress, Okay, and if it is not ready to compress, so density will be constant. This is called low speed flow, and for this Mach will be less than 0.3, and this is the high speed. Okay, high speed flow. So like we have piston. Okay, this is the cylinder here. We have piston. This is the piston now. Okay, and this piston, if you apply force, okay, if you are applying force here, so it is not ready to move in forward direction. Why? Because inside this cylinder we have filled the incompressible fluid. So that piston is what not ready to move in forward direction. Why? Because of this fluid. This fluid will resist that motion. This fluid will resist the motion. Okay. It is not ready to compress. This fluid is what not ready to compress. Not ready to compress means high resistance. Fluid is what applying high resistance force. Okay. What is the example? Example is water. Now, water is the incompressible fluid. What is the example for this? Air. Air, or you can say gas. So gas or like air, it allow a compression or easily ready to compress. Okay. But what about water? Water is what always considered as an incompressible fluid. Why? Because that water will not allow compression. It is totally depends on the basically one term will come that is called bulk modulus. So bulk modulus for the fluid, for incompressible fluid, will be very high, or it approaches to infinite. And then what is the bulk modulus? It is the resistance. Okay, resistance for the compression. What is the bulk modulus? What is the bulk modulus? Bulk modulus, it is resistance to compression. Okay, resistance to compression means if you are trying to compress it, then bulk modulus means it will try to resist it. The resistance to compression called bulk modulus. So it is very clear for the incompressible fluid, bulk modulus approaches to infinite. Approaches to infinite means what? It is very high resistance for the compression. Very high resistance for the compression means it is not ready to compress easily. If it is not ready to compress, means it becomes incompressible. Hope you understood. So bulk modulus, it is denoted by K. Okay, and bulk modulus, it is the fluid property. So like for the air, bulk modulus will be very less. If it is very less means it will not apply, it will not provide resistance for the compression because bulk modulus is very less. All right, if it is very less, it will not resist the compression, means it will ready to compress. Okay, that fluid will ready to compress like air. So high resistance to the compression means high bulk modulus. So for the incompressible fluid, it is approaches to infinite, because incompressible fluid, it is kind of the ideal fluid. Okay, if it is ideal fluid, then 100% bulk modulus will be infinite. Ideal means what? It is not going to compress even 1%, 0.1%, it is not going to compress. It will not allow. Like water, you can say, if you are going to apply thousand of the uh, bar pressure you are going to apply for the water, then density will change little bit. I mean, it will little bit, it will allow compression, but you can think about the applying pressure. It is huge, thousand of bar I am saying to you, or Newton per meter square. No? One bar means 10 to power 5 Newton per meter square, or 10 power 5 Pascal. Okay, so overall you should know like what is the incompressible, what is the compressible, so that definition you know, but you are not going to write definition all time. That understanding is very important. Okay, if I say compressible flow, so don't tell the definition. It is defined as the types of the flow where density is what constant with respect to space and time. No, this is what old definition. It is kind of semester point of view definition, because definition is also important. If you are not going to write definition properly in your semester exam, that faculty will not give marks. That is true, but now you are preparing for competitions, your mind should work for like centralization will be there. I mean, you have to answer like this. Incompressible means first thing comes in your mind, that is it is not going to compress. It is not going to compress means what is the physical meaning of it? It means density is not going to change, means density constant. If density constant, then why it is not going to compress? Because resistance to compression is what, very high. If it is ideal fluid, then it is bulk modulus approaches to infinite, exactly infinite for the ideal fluid, because ideal fluid is what, not possible, it is just approach. Understood? Hope it is clear to everybody, right? Fine. So compressible, incompressible. Now rotational and irrotational. Okay. And I think one more thing need to add here. Should be added here. 7 number. Viscous flow. Okay. Inviscid flow. So before going to rotational and irrotational, I will explain viscous flow first. Okay. You change the number. I must say it is 5. So what is the viscous flow? So viscous flow or viscous fluid. Okay. So what do you mean by viscous? So viscosity term you have seen many times. So viscosity, it is a property of fluid. It is property of fluid, and what this property will do, what it indicates, it is the resistance to the flow. How it will resist one layer to adjacent layer. There will be resistance. One layer to adjacent layer. There will be resistance. Got the point? Okay. So see, resistance to the flow and resistance to the compression, there is a big difference. No? This is what? Resistance to the flow, and this is what? Resistance to the compression. Yes or no? Resistance to the compression means it indicates the bulk modulus. Resistance to the flow means it indicates viscosity. It is denoted by mu. Okay, two types of viscosity you have: dynamic viscosity and kinematic viscosity. That will tell you later on. I believe that fluid mechanics you know. No? Anyway, so resistance to the flow is called viscosity. Okay, so like flow field we have like this, and this is what viscous flow. If I will draw for the viscous flow velocity profile, if I will draw, this is the velocity profile. Okay, this is velocity profile for the viscous flow. If I will draw it, so it comes like this. Check. So like this. Okay, this is the velocity profile. So what is the mean of it? If you check here, we have at this point velocity is what, 0, because this, see here, it is starting from origin, that means it becomes 0. What about this next? It is u plus du. What is this? It is u plus du plus du dash. I mean, again increment is there, yes or no? So velocity is what going to change. That means resistance to the flow means what? It will try to oppose the flow. So initially it was 0, then velocity is what going to increase and increase. So why it is happening? Why this velocity profile you are getting? Because of the viscosity. Well, there is only one reason. It is called viscosity. Understood? Might be you heard about Newton's law of viscosity. I am actually not Newton's law of viscosity. These are the fluid mechanics part. I am not going to enter in that part. Otherwise, one more hour it will take. Okay, in short, I am just going to explain. So what was there? It was tau directly proportional to du by dy. This was shear stress. Do you remember this shear stress? And this was velocity gradient. Yes or no? So if you remove this proportionality, then you will get tau dy. This mu is nothing but dynamic viscosity. Okay, in short, I am saying. So this velocity gradient, why you are getting? Actually, this is what? This axis is what? Y, and this axis is what? X. So in y direction, check that velocity is what, changing or not? See, here it is u plus du, and here it is u. If I will check what changes of the velocity you are getting here in very short length in this. So it is nothing but, suppose this distance is what, dy, and what is the change you are getting here? So here velocity is nothing but u plus du. Okay, so you can say u plus du, that upper layer, and lower layer, it is starting from origin, which is nothing but u. Okay, so if you get the difference, so you may get that change of velocity du. Understood or not? Upper layer, here you can say u plus du, and at origin it is 0, but still velocity you are indicating by u. Yes or no? So what is the difference between one layer to another layer? It is du. So du velocity difference you are getting in dy distance. If you write gradient, gradient is what? That quantity changing with respect to length or space, that will be called gradient. So if velocity is changing with respect to length, then it will be called velocity gradient. If temperature is what changing with respect to length or space, it is called temperature gradient. If pressure is what changing with respect to length or space, it is called pressure gradient. Hope you understood. In short, I am explaining this. So this is the Newton's law of viscosity. So this mu is nothing but dynamic viscosity. So this dynamic viscosity basically called yes, dynamic viscosity called resistance to the flow. All right. So now, what is the inviscid flow? What is the inviscid flow? That inviscid flow is what? Just a reverse of the viscous flow. No? You just check number. Inviscid flow. Inviscid flow. What is the inviscid flow? It is reverse of viscous flow. Reverse of viscous flow. Yes or no? Reverse of viscous flow means what? Not provide any resistance. Not provide any resistance. Not provide any resistance. Resistance. No? See, to the flow. Yes or no? Because viscous flow means viscosity will be there, and viscosity is what? Resistance to the flow. But if it is inviscid flow, so layer to layer, adjacent layer, better to say adjacent layer, adjacent layer will not provide adjacent layer will not provide any resistance to the flow, right? And inviscid means what? Dynamic viscosity, because if it is not providing any resistance means viscosity will be zero. That means viscosity will be zero. Yes or no? Yes. So if viscosity is zero, then whatever the flow pattern I have shown you, this is the fluid flow, and if it is this fluid flow is what? Inviscid flow or inviscid fluid. Then if I will draw the pattern, then how that pattern will you may get? You may get pattern like this. See, that velocity will not be changing. It will be the inviscid flow. This is what? Inviscid flow. Mu is zero. So check everywhere velocity is what? Constant. Huh? Velocity is what? Constant. If velocity is what? Constant, then what is the mean of it? That velocity gradient you will get zero. Means what? You will be constant. See, du by dy equal to 0 means what? U is equal to constant, means velocity will be constant. That's the mean of the inviscid flow, means that velocity is what? Not going to change profile. That profile will not be changed. Understood? It will be constant like this. All right. So that is called inviscid flow, reverse of viscous flow. Now, what do you mean by rotational flow? Rotational flow. So rotational flow means what? Rotating about center of mass. Okay, each particles. What rotating? Each particle. Each particles rotating about its own axis. Okay, each particles rotating, or each particles are, okay, grammatically, okay, each particles are rotating about its own axis, called rotational flow. Called rotational flow. In viscous flow slide, what is the mean of it? What is the mean of it? What you are saying? Okay, rotating about center of mass. Oh, check. Right. So basically, you always remember, okay, that like for that reason, if you are having boundary layer, okay, here. So this is the basically, if I show the boundary layer, wait, if I show the boundary layer, so it is kind of if this is the boundary layer, okay, so you can say that exit, like inside this their velocity is what? Changing, but outside the exit will be what? Velocity gradient will be zero. That's the reason even for the viscous flow also, but if you draw the boundary layer, so there is the certain reason where flow will be viscous, and after that it becomes inviscid flow. Why? Because you may get that like that will be decided, yeah, boundary layer thickness and all. So if you talk about the boundary layer formation, so that boundary layer formation you will get always in case of the viscous flow, because boundary layer formation will be because of the viscosity only, because of the resistance of the flow only. That I will tell you in when I will separately take class for the boundary layer theory. Okay, so now what I wanted to tell, let me complete this, otherwise it will be skipped. Anyway, so each particles are rotating about its own axis called rotational flow. Okay, called okay rotating about center of mass. Each particles are rotating about its own axis called rotational flow. And when it will be possible, I will explain first. I will write it is possible when the flow is what viscous flow. Okay, when the flow is what viscous flow, so that time only rotational flow will be possible. Means for rotational flow the dynamic viscosity will not be zero. Sorry, it is will not be zero, not constant, will not be zero in case of the rotational flow. Okay, in case of the rotational flow that dynamic viscosity will not be zero. Now just try to understand. Suppose this is the fluid flow. Just let me clear this part, it is very important. This is the fluid flow. Okay, so for this fluid flow I can take one part, and that part is what rectangular fluid particle. So this is the rectangular fluid particle. Any part I can take. So this part I have taken, this is the rectangular fluid particles. This is the rectangular one fluid particle. Check. Okay, this is the rectangular fluid particle. So if I'm saying rotational flow, that means this fluid particle should rotate about its own axis. Okay, for this fluid particle, suppose axis is what center of mass, so it is center point. This is the axis for the this fluid particles. Okay, now why it is rotating? Very simple. It is rotating because that shear stress, I explained you, shear stress always Newton's law of viscosity. So if it is the viscous flow, okay, if it is viscous flow means tau will not be zero. Tau will not be zero for viscous flow, and tau will be zero for inviscid flow. Till now it is very clear to you. There should not be any confusion. See, dynamic viscosity will be zero for the inviscid flow. So inviscid flow means tau equal to zero, because mu will be zero, dynamic viscosity will be zero, means tau will be zero. What is tau? Shear stress. Shear stress always acts on the surface. Suppose this is the surface, so shear stress will be acting like this. Now if it is normal stress, then it will be perpendicular to the surface. If it is shear stress, then it is tangent to the surface. That's the reason shear stress will also be called as tangential stress. In other words, tangential, it is called tangential stress. Okay, it should be very clear. So if it is viscous flow, that means tau will not be zero. If tau will not be zero, because I told you rotational flow will be viscous flow. So let me complete this. If it is rotational flow, so it must be viscous flow. If it is viscous flow, so definitely shear stress will be acting like this. So it is like making one tangential force, because shear stress into surface area will give the shear stress into surface area will give the shear stress into surface area will be shear force. What is shear force? Is equal to shear stress into area, surface area. Okay, shear force unit is what? Newton. Stress unit is what? Newton per meter square. Area unit is what? Meter square. Understood? So this shear stress tau and this tau, top and bottom, okay, over the surface will have a shear stress. Shear stress and that area will give the shear force. That shear force about the center point. I will show another diagram. Check. This is the one shear stress into area, which will be the force. I say shear stress tau 1 F1, and this is just opposite. Tau 2 into A will be F2. Even though F1 and F2 both are in magnitude, it is same, because shear stress and in fact area will be same. Okay, even though shear stress is same or not doesn't matter, but whatever the F1 and F2 you will get, it is just opposite, and this is the center point for the particles. It will give one rotation. Got my point or not? So that this is the particle, this is what fluid particle. Huh? This should be very clear there. This is what fluid particle. Check. I must show you like this. This is the diagram. This is the fluid particle. So over the surface there is the one shear stress. Shear stress will exist. Why? Because it is the viscous flow. Shear stress bottom, shear stress, this is the top surface, and this is the bottom. So top surface shear stress or shear force, this is shear force. Okay, and bottom shear force will give the coupling moment. Okay, and that will give rotation. Okay, and this fluid particle will start rotating. Fluid particle will start rotating about on axis. Understood? Yes or no? About own axis. So it is very clear now. If you are then it is start rotating about own axis, then this type of flow called as rotational flow. So for rotational flow, what is the important point? Rotational flow will always be viscous flow, or in other word you can say only viscous flow can be a rotational flow. Yes or no? Only viscous flow can be a rotational flow. Both is correct. If it is rotational flow, it means it is viscous flow, or you can say only viscous flow can be a rotational flow. Hope you understood. Because in viscous flow only you will have a shear stress, and if you have shear stress, then shear force will be there, and if shear force will be there, then definitely force into perpendicular distance will give moment about the axis. That's the rotational flow. Coming to irrotational flow. I can say this is what reverse to rotational flow. Yes or no? That means what is the meaning of reverse to rotational flow? Means it is not rotating about own axis. If I say it is means what? Fluid particle. Fluid particle is not rotating. Okay, is not rotating about their center of mass. Okay, it is not rotating means why it is not rotating means there is no shear stress. Why there is no shear stress? Because there is no dynamic viscosity. Okay, so indirectly what? Indirectly means irrotational flow is what? When mu will be zero, when it is inviscid flow. Okay, this is the conclusion. Understood? This is the conclusion. Always remember. Okay, I think this is 7th or 8th point. You check it. Always remember two things are very clear, and that you need to remember. Okay, that rotational flow will be a viscous flow always, or reverse also, and irrotational flow will be inviscid flow, or reverse also possible. Inviscid flow will be irrotational. Understood? Yes or no? So I can write again: rotational Okay. Rotational flow, that means viscous flow, and arotational means means inverse. That reverse also happens. Done. Okay. So, all right. So next session will be continuous. Thank you. Thank you all.